Okay, hello everybody. It's wonderful to see such a good crowd here today to welcome back one of our star CME graduates back to Stanford. Paul, I'm
Thanks.
Glad you could visit.
A star or an asterisk, we're not sure which.
Well, when we think of Paul Constantine, we can't help thinking of another star student who's mentioned here. And the reason I think of him, David Glark, is because he and Paul both handed in their thesis within what?
Within an hour.
Within an hour of each other. But also because they're very much two of a kind. They're very lively and creative fellows, and we've been missing them ever since they graduated. But luckily, they keep coming back every so often. Chi-Chi really is probably another one like you too, Paul. And it looks like you'll mention him too.
Oh, sure. Yep.
Okay, well, Paul went off to the Colorado School of Mines. Oh, yeah, it says that. Mm-hmm. So luckily not too far away.
Yep.
So welcome back, Paul.
All right, thanks, Michael.
Thank you for coming.
Yeah, thanks everybody for coming. If you don't have a handout, I've got spares down here, so you'll have to walk down in front and everyone will see you and you can pick up a handout. Thanks for coming. I'm going to talk about some work that I'm really excited about. Active subspaces, emerging ideas for dimension reduction and approximation, integration, and optimization, and we'll get to all those terms eventually. This is me, Paul Constantine at Colorado School of Mines. It's M-I-N-E-S, not Minds or Mimes. Some people get confused sometimes. It's a little engineering school in the foothills of the Rockies in Golden, Colorado. It's a beautiful place to work. You can find me on Twitter at Dr. Paul Enomial. That's fun, right? In fact, my tradition is to take a picture of the room, and then we'll post it on Twitter. Ready? So say something. Say subspaces. We'll see if this gets everybody. All right. Great room. You guys look good. Oh, you blinked, so no, I'm just kidding. All right, so some of this, a lot of the work, the references and the codes and some videos can be found at activesubspaces.org that we just put up. This is joint work with lots of people. The two people that I'll mention here, Chi-Chi Wong, who's at MIT now in AeroAstro, and David Gleick, who's at Purdue. They're sort of my sounding board with this work. Whenever I have an idea, I call them or G-chat them or do something, and I'm like, hey, what do you think about this idea? And they say, well, you have to fix this part, and then we go back and forth, and it's just great working with them. Some of this work with active subspaces actually started here at Stanford at the 2010 summer program for the Center for Turbulence Research, working with Gianluca Iacarino and Chi-Chi and Ali Reza Dustan. That's where a lot of this work started. Back in 2010. So this work is supported by Department of Energy, Office of Science, Applied Math Program. This is my standard disclaimer. These slides are meant to complement the oral presentation, so watch the YouTube video and use out of context at your own risk. Okay, so I'm here for one thing, which is to plug the book. So I just wrote a book on the subject. It was published by SciAm in this new series called Spotlights, which is supposed to be a rapidly published series of short books on new ideas. That's why I was able to do it, which was really exciting. It's normally $39 since you are all here. How many of you are SciAm members? Okay, most of you. Good. So if you're not a SciAm member, you're in luck because I got the SciAm office to give you a coupon code to get you the member price of $27 just for being here. So cool, right? Here's the URL where you can get it. I also was, one of my goals for the week was to bother the library. So the Stanford Library is going to buy a copy of this book. So there's one in the library. You can also download it from the website. If you're on the Stanford network, you'll get PDFs of the chapters. So read up, study up. Okay, so let me do a movie that is the entire talk in 1 minute. That's what I wanted. And this. Okay. So here's the idea. Let's say we have a bivariate function, a function of two variables. and we're going to look at this function from the top, and what we want to do is approximate this bivariate function by a univariate function. How are we going to do that? First, we'll sample the gradient of this function randomly throughout the space. So we get a bunch of arrows all represented by the gradient. We combine all those gradients, and we identify a direction along which the function changes primarily, an orthogonal direction where it's relatively flat. Then imagine rotating the function so we're looking at it along the direction of the inactive variable, and we see the variation along the active variable. We'll now pick points in this space of the active variable and come back here to the full space and draw some samples of this function along the inactive space for each of these points. And what we're going to do is compute conditional averages with these samples here. So we bring this back to our perspective of looking at this function. We collect all of our function values. We compute conditional averages of these points, which are the blue dots. And now we have a set of data that we can fit a univariate response surface to, a univariate surrogate model, a univariate polynomial, whatever you want to call it. And now we can use that throughout the entire space as a bivariate approximation. So that's the whole idea in pictures. So all the math and all the notation that we're going to go through is basically that idea, but generalized. And so you all have the poster in front of you. A lot of the notation that I'll go through on the slides is also on the poster. So feel free to look down there, and feel free to ask questions too as we go through this. All right. So this is how I see the world. I think of the entire world as f of x. Let's talk about what f of x means to me. Let's see. For one, you can think of this. I know several of you in here, and several of you work on really large simulation codes that model big complex physical systems. Think of this f as your quantity of interest, the scalar valued output that is the quantity of interest from your model, and these x's here is a vector of the inputs to your simulation. Let's see some other things about this. We're going to assume that this is that the variables are continuous, so I'm not working in discrete variables. We're going to say the function's nice and smooth, because otherwise in high dimensions it's hard to do anything. So it's smooth, it's differentiable. What else? These x's are really important. We're going to assume that they're centered at the origin. So we're going to scale all of your inputs so that they're nice and normalized, centered at the origin, and the variation of these inputs is going to be about the same, and they're going to be able to vary independently. So there's not really any correlation structure in this space of the x's that you could maybe do some other kind of dimension reduction. We assume we got rid of that already. So these are all independent parameters with about the same range of variability. So what might your f of x be? I'll tell you some of the f of x's that I've worked on, and then maybe you can think of your own f of x's and keep them in your mind as we go through the talk. So just recently, Trent Lukács gave his defense yesterday, and for him, f of x was the drag or the lift from a wing or some kind of supersonic vehicle, and the x was the shape parameters of the geometry of this vehicle. With Gianluca and the PSAP program, F was the pressure at the exit of a scramjet, the combustor of a scramjet, and the X's were the flight conditions. Some other ideas that I've been working on with Reed Maxwell at Mines, F is the runoff from some kind of hydrological system, and X represents the subsurface permeability. Another example that that I've worked on is F is the maximum power out of a photovoltaic solar cell, and X is the circuit properties. So these are the kinds of things that I think of as F of X, and I assume you guys all have your own F of X's. So what do we want to do with this F of X? Typically, I live in this strange world of uncertainty quantification. A lot of times the things that we want to do when we're trying to quantify the uncertainty in these kinds of models is to study the variability of the output given the variability of the inputs. And that might take the following forms. We might want to build some kind of an approximation of f of x, something that's a good approximation globally. So some kind of like large response surface over the entire space. We might want to integrate over the entire space to get the average of this quantity of interest, or maybe we want to get some kind of minimum of this function. Max and min, understand the range of the outputs given the variability of the inputs. Okay, so these are global computations. We don't know much about this F. All that you know is that you have some kind of computer code, and given inputs, you can compute outputs. We don't know a lot of structure ahead of time. So if we want to do these kind of global computations, they're really hard in high dimensions. And so let's try to get a sense of what that means of being hard in high dimensions. Basically, it just means it's going to take a long time. So let's do a little back of the envelope thought experiment here. Let's say we have one dimension, And some of you do CFD. What kind of resolution do you need, like in your spatial dimensions? If you had 10 points per dimension, that would be a relatively coarse model probably for most of your models. But let's say that we're going to do 10 points per dimension here. And let's say that our model is super, super fast. So given inputs, given this one value for the input, it takes 1 second to compute the output. OK, so 10 seconds in one dimension, not a big deal. 2 dimensions, we're still doing OK. We want to do 10 points per dimension. We get to about 1.5 minutes. That's all right. You get to 3 dimensions, and all of a sudden, well, you go take a coffee break, no big deal. Your study finishes. You come back. Oh, gosh, you get to 4 dimensions, and now all of a sudden you need 10,000 runs to do 10 points per dimension, and it's going to take 2 and nearly 3 hours to complete your study. It only gets worse. So 5 dimensions. The 5 dimensions you might think is a relatively small number of dimensions depending on the kind of problem that you're solving. But for these kinds of global computations where you're averaging or trying to find a global optimum, you need to search the entire space because you don't have any structure on your function. Now you're at a day. 6 dimensions, you're at a week and a half. 20 dimensions, 3 trillion years. This. You're calling 20 dimensions low, and I'm saying that if you want to do an integral or explore a 20-dimensional space where you really have 20 points per dimension and your function evaluation takes 1 second, it's 3 trillion years. It's just the curse of dimensionality. Yes. Ah, yes. Great segue. I appreciate that very much. You've got a great seat right there. I hope you keep asking questions. OK. So yeah, so maybe you argue with this. This is the curse of dimensionality, right? This is why these studies are difficult in high dimensions, because you want to get some global sense of your function over a high dimensional space. You don't have any structure that you can exploit necessarily, and this is what happens. Okay.
I mean, if you're going to take comments from the floor,
yep.
There's enormous structure in physical problems.
Yeah.
They're not just random values on a 20-dimensional grid.
Right. Yes. Yeah, so we'll get to those examples. I mean, you are setting me up to knock it out of the park with the active subspaces. So thank you. So
you also forgot we have computers with 150 million cores on them.
It's true. I didn't do any parallelism here, but here is my point. Let's say that we want to reduce the time it takes to compute one function evaluation. So this is the idea of like reduced order models, right? This is some of the stuff that people in Charbel Farhat's group work on. It doesn't help with this exponential scaling, right? It might help if you have a fixed dimension, you know how many points you need to take, you reduce your computation by a half, or you reduce it down to 10% of what it was before by using a reduced order model, that's a win. But it doesn't really help with this scaling problem. Maybe you can do better designs. Maybe you can do something like Monte Carlo. Or maybe you can exploit some structure in your model. Maybe your function can actually be well represented by a sum of univariate functions. In that case, sparse grids work really well. Maybe your function doesn't vary a lot along most of the dimensions, and it does vary along some of the dimensions. You can build some kind of adaptive approximation. But again, the problem with adaptation is that you have to be able to check a little bit in every dimension if you don't know anything ahead of time before you can decide which of those dimensions are important. Even if you know ahead of time, even if you have a physical sense that some variables are not important, you have to be able to check which ones are important, right? And this is still that global kind of computation. Low rank is another type of structure that people try to exploit to break this curse. But you don't, if I just give you an f of x, you might not necessarily know that you have that low rank structure ahead of time. So for me, this is where the real bang for the buck is doing the dimension reduction. And I want you to think of dimension in a log scale. I want you to think of it like a Richter scale, right? If you have a function and you don't necessarily know anything about your function ahead of time, then be afraid of dimension increases, because really studying, trying to understand which variables are important can be really, really expensive in high dimensions. But if you can, if there's a way to do it, then I want to argue that this is the place where you want to try to cut down, as opposed to doing a better design or reducing the value of or reducing the time of your simulation. Okay. And so a lot of the ideas that are out there, one idea you might think of that I sort of alluded to already is some kind of sensitivity analysis. You say, well, I have 20 dimensions, but really only 3 or 4 are important. So let's see if I can get back down to this sort of 3 or 4 range by identifying those important parameters. And this is sort of where active subspaces come in. So the active subspace is a generalization of this idea of trying to find the 3 or 4 most important parameters. Instead of finding the 3 or 4 important parameters, we're going to look for important linear combinations, which is, I say it's a generalization because if the weights of your linear combination are 1s and 0s everywhere else, then you return back to this coordinate-aligned kind of system. But otherwise, if you have weights that take non-trivial nonlinear combination or linear combinations of these things, then you get some really powerful dimension reduction. And so the key contributions of active subspaces are to generalize this coordinate-based reduction to linear combinations, and also to formalize how to properly ignore the unimportant linear combinations. And this is where the cool math actually comes in. If you have a system with 5 parameters, you want to ignore 2 of them, and they're all independent, you set those 2 at the nominal value or something like that. It's not too difficult. But when you start doing linear combinations, then how to properly ignore the unimportant linear combinations becomes really important. Okay. So let's be a little bit more formal. So let's say that we've got our function f of x. X is some kind of vector in m dimensions. I also have a gradient vector. So my gradient vector is also a vector in m dimensions. And I'm going to assume someone has given me, or I have found some way to choose a weight function on the space of the inputs. So this is, you can think of it as a probability density function. It's going to be positive, return positive values. And now I'm going to introduce you to a matrix. So this matrix that I'm going to construct is the outer product of the gradient. This is a symmetric matrix. It's rank 1 at one particular point locally. But if I average this matrix over all of the x's, then I get a matrix that's symmetric. It's positive semi-definite. It's not necessarily rank 1 anymore. But I can take its eigenvalues and eigenvectors of this matrix. Okay, so when you take eigenvalues and eigenvectors and you see some structure in the eigenvalues, let's say we find that a few of the eigenvalues are really large and the rest are relatively small. I'll partition those eigenvectors accordingly, and this is going to give me a change of coordinates for my input space, for the input space of f of x. So this W1 here is going to be a tall matrix with m columns and n rows, and n is less than m. And now I can do this rotation, just like I did in the movie. So I've got x, I multiply by the identity matrix, I break things up according to my partition, and now I can define these new variables, y and z. I'll call y the active variables, I'll call z the inactive variables. And we'll get to y here in a second. So before we go any further with this construction, I want to do a really quick comparison. So you've seen covariance matrices, right? If I had taken x transpose and I average that, I get the covariance matrix of x. Remember my assumptions on the x's that they're already independent, right? This matrix is going to be a diagonal matrix. There's not going to be necessarily any decay. It's probably a constant diagonal. I don't get any reduction from doing something that's covariance-based, which might be principal components or some other kind of covariance-based reduction. This matrix, in contrast, is a matrix that is directly related to the f, to that function, to the output, and in particular its gradient. So they're different. Okay, so here's a really nice relationship between the eigenvalue that I'm computing for this active subspace and the gradient. So the gradient here is the squared directional derivative along the eigenvector. If I average that, I get back the eigenvalue. Okay, so we can extend this a little bit further. So if I take those coordinates y, the active variables, and I take the squared 2 norm of the gradient along the active variables, that's the sum of these first eigenvalues. The squared gradient along the inactive variables is the sum of the rest of the eigenvalues. And now we're at a point where we can say something about the function, right? These eigenvalues here are properties of the function. They come along with the function. It's like a Lipschitz constant. It's like a Fourier coefficient. It's properties of the function. So if I can measure these and identify a few large ones, let's say if these guys are actually 0, let's say they're exactly 0, then I have found all these directions in the input space where the function is constant, right? And I want to ignore those. I want to find a way to ignore these directions where the function is constant. There's a reason that there are more scenic photos of mountains than there are plains, right? Because mountains are interesting and plains are boring. And so what we want to do is find a way to look at our function and think about it in terms of the directions where it looks like mountains, where there are changes happening, and ignore the directions where it looks like plains. Okay, so how are we going to actually measure these things? We need to compute these eigenvalues somehow. And I propose a sampling method. And so now we're back to the Monte Carlo case. So I'll draw samples of my inputs according to that given density function. For each of those inputs, I'll run my simulation. I get the output, the lift or the drag, for example. And let's say that I can get the gradient. Maybe I have an adjoint solver. Maybe I have automatic differentiation. I can get the gradient at that point, xj also. Now I can do basically a sample approximation of that matrix C by combining all these things into a matrix that approximates C, and I can take the eigenvalues and eigenvectors of that matrix, which are then estimates of the things that I actually want to compute. And now we're in this place where we have estimates. We want to know how good those estimates are, so let's get to that. One comment: doing this is as long as the number of samples is larger than the number of dimensions, then doing this kind of construction is equivalent to stacking up all my gradient vectors, taking the singular value decomposition, then my left singular vectors are the eigenvectors I was looking for, the singular values are square roots of the eigenvalues that I was looking for. So this idea, without all the context of before, showed up in Trent Russey's 2010 PhD thesis. He called it the active subspace method. While Chi-Chi and I were sort of putting this together, I found this, and I thought, well, it's a catchy name, and we should credit him, and that he was doing something like this before, and so we've been calling it active subspaces since then. Okay. Oh yeah, we need to estimate the variability in these things, and in practice we end up using a bootstrap. So you can use, especially in this formulation, it's really easy. You just sample with replacement from these columns and recompute these as bootstrap replicates, and you can get some idea of the variability in these estimates. Okay, but we want to know formally, like, how many samples do I need to get a good estimate of the eigenvalues? How many samples do I need to get a good estimate of the eigenvectors? So some of the work that David and I did last summer, the paper's in revision right now with SciMax, is applying some of the work by Alex Gittins and Joel Trope. They used non-asymptotic random matrix theory to look at random matrices and study how close estimates of a random eigenvalues of estimates of a random matrix were to the true population eigenvalues that you want to estimate. So if I choose n, big omega means that this is a lower bound. So n is greater than or equal to a constant times this thing. What are these things? So m here is the dimension. So this scales like log of the dimension, which is really nice. Here is our relative accuracy in the eigenvalues that we want to compute. We had to assume that our gradient was bounded. So L squared here is the squared norm of the gradient over the entire space. And if you can choose this many samples, then you get this nice result that with high probability, your eigenvalue estimates are bounded or the relative error is bounded by epsilon with high probability. Okay, so that gives us the eigenvalues. How about the eigenvectors? So we can combine that result about the eigenvalues with some standard results from eigenvector perturbation theory. And we get a similar kind of bound. I have my first eigenvalue here, same log of the dimension. And this tells me that the distance between the true subspace, this is a shorthand notation for the distance between the true subspace and the estimated subspace, is bounded by this quantity. So here's the same epsilon, so we've controlled for the error in this thing. The thing that's really scary is that this depends on the spectral gap. So if you have eigenvalues that are really, really close together, then this upper bound increases and your estimate of that subspace gets worse. And we see this happen in practice too. This is not just an upper bound that's not tight, like this is actually happening with the subspace errors. So we're always looking for big gaps in the eigenvalues because that tells us that we can estimate that subspace really well. Okay. So now I've talked about eigenvalues, I've talked about eigenvectors. Let me stop for a second and just be abundantly clear about the kind of problem I'm trying to solve. I don't really care about, for example, a low-rank approximation of this collection of gradients. That's not my aim. I don't care if you're thinking about this in like a model reduction sense, in a proper orthogonal decomposition. I don't care about some low-dimensional linear subspace where the gradients might live. That's not my aim. My aim is to approximate this function of many variables by a function of fewer variables. And in particular, the model I'm going to use is a function of a few linear combinations of all the variables. So this is the goal. And so now let's move from that. From now on, we're just going to assume that we've got that subspace, or at least an estimate of it. And we want to know how to use it and what are the effects of using it as opposed to using the full function. Okay. So here we are in the approximation phase. And maybe I should warn you at this point. I said approximation, integration, and optimization. The approximation is the most mature of this work. The integration and the optimization are still sort of emerging ideas, right? So that's just kind of a caveat. Okay, so here is the model that I want to use. I want to say that I can approximate this function of lots of variables by a function of a few linear combinations of the variables. And so the questions that arise are, how do you construct that function? How do you build G? It's not a linear function. It's going to be a nonlinear function in general. What is the approximation error? What does that approximation sign mean? And then what is the effect of using this W hat as opposed to using the real W? So these are the questions that I want to ask. And let's restrict ourselves to the following case. We can generalize from this case, but this is kind of the most interesting case, at least from the ones that I've looked at. So let's say that our x's are actually bounded in a hypercube. So all our x's are bounded between -1 and 1. And I've got a uniform density function on that space, 2 to the minus m, because I want to integrate it so that, or I want it to integrate to 1, so that's my uniform density function. Okay. This case is really interesting because if you start with a cube, and then you do a rotation, and then you project that rotation to a lower dimensional space, you don't get a cube anymore. You get this thing called a zonotope. So imagine that you've got a cube and you rotate it and take a picture of it. Now the two-dimensional space that I want to use from this original three-dimensional space looks like this six-sided polytope here. Right? So here's m is equal to 3, and this is the set. You can write it in set notation really nicely. It's just the set of the y's where the x's come from this cube. Let's see if there's anything else to say. Oh, and then from this, if you can identify these sides, now you can describe the space of the y's by a set of linear inequality constraints, which is really helpful if you're doing optimization, for example. But let's look at what happens when m increases. Okay, so now what you are seeing the silhouette of a 5-dimensional hypercube on a 2-dimensional screen here. And so this is what it looks like at 10, a 10-dimensional hypercube. How many corners are there? There are 2 to the m, so 2 to the 10 corners. A bunch of those corners are in the interior here, and some of them form the convex hull of this shape. If I go to 20, it starts to look like this. If I go to 100, it starts to look like this. This is pretty cool. It actually turns out it starts to look like a circle, and I actually think in most physical problems, because of the physical variables, it won't look like a circle. This is because I'm taking random projections just to make the picture happen. But I think there's some really interesting stuff going on here that if we take the limit as m goes to, or as m gets large, this will look more and more like a circle. Anyway, I think that's cool stuff. The other thing that we have to deal with, so we have the domain of this function g. Before we construct g, we have to know what its domain is. The other thing that we have to deal with is that we've got x's, and we can get from x to y pretty easily, right? You just multiply by W1 transpose. But we have this issue that if we want to choose some y's and then go back to the x's, then it's an underdetermined problem, right? This is the W transpose is a fat matrix, and these have bounds on them. And so now the question is, how do we choose, given AY, how do we choose an x that corresponds to it? Or maybe you want to choose a lot of them. And so this is something that we have to deal with when we construct that g function. Right? This is a real issue. Why do we need to do that? Because remember, our function is a code that takes x. Our function, the simulation code that you have takes x. It doesn't take y. I don't know, if you have, let's say you're running a climate model and you have a linear combination of your cloud parameter and your grass parameter, and you set that equal to 0.5, then how do you run your climate model from that? You've got to figure out how to go back to the x's from the y's. Okay. Let's talk about how we'll do that in the case of approximation. So we're going to do that with conditional averaging. So I'm going to construct my g of y to be a conditional average of f. This expression here is just x, so this is just f of x, but I'm going to average over all of the z's that correspond to the given y. And then I will use that construction to be my function of a few linear combinations. Under this construction, we have a really nice error bound, which is that the root mean squared error is bounded by a constant times the square root of the sum of those eigenvalues that correspond to the inactive variables. It took us a while to get this construction right, but once we got this, we're able to derive that, and we're really excited about that. You might be concerned that for a given value of y, now I'm asking you, okay, every time I give you y, you have to integrate over all the z's, so we're back to this high-dimensional integration problem. Well, we're in luck. We're actually excited about a Monte Carlo approximation of that g. Why is that? Because the variance along those inactive variables is relatively small. So we feel like we can get away with a simple Monte Carlo, a few function evaluations to estimate this conditional average with some kind of Monte Carlo approximation, where now the z's are drawn according to this conditional density. Now, if you build things this way and you can actually draw these independently, then we get another error bound that looks just the same, except we've got the same constant, which is the Poincaré constant that deals with the domain, but now I've got a 1 plus, say, 1 over root n. But I still have a multiplication times the square root of the sum of these eigenvalues. What that means is if your function, whatever your function is, if these are 0, then this Monte Carlo approximation of this conditional average is perfect. It's a perfect reconstruction. And why is that? If you want to take the average of a constant, how many times do you need to evaluate it? Just once. Right? If you know that your function of 1,000 variables is a constant, then it's really easy to do all these things. Right? So that's what's going on here. That's why we have this, this term where this entire error could be 0 with this Monte Carlo approximation. Okay, so what happens when we have estimated subspaces, right? We don't have the exact W's. That was all assuming we have the exact W's, we can prove nice things. So if I actually have estimates of the W's that I get from that Monte Carlo approximation, there's some error there. Here's what happens to that error bound. Here's the, I'm back to the old G, back to the OG here. And now I've got estimates of my eigenvectors, and here's what happens to the error bound. Here are the inactive variables again. Oh, sorry, the eigenvalues that correspond to the inactive variables again. But now I've got another term. And that other term here is the square root of the sum of the eigenvalues that go with the active variables times the subspace error. And this is something that came up a lot in Trent's work, that if you don't get this subspace right, if this epsilon isn't small enough to dominate the big eigenvalues, then you can potentially have a lot of error. Right? So it's really worth your while to take a lot of time and get this subspace, get this epsilon small, which means looking for gaps in the eigenvalues. So if you want to choose the dimension of your subspace, we haven't talked about that yet, but you want to look for gaps so that this epsilon is small here. Okay, so here's the big picture and big ideas. So some of you are kind of drifting off. Oh my gosh, so much notation on the screen. All right, here it is in bullet points. I want to choose points in the domain of G. I know what that is. It's this funny thing called a zonotope now. I pick some kind of a design in that space. I'll estimate the conditional averages for each of those points. So for each design point, I'll do a few simulations to estimate the conditional averages, and now I'll construct that approximation on n less than m dimensions. Voila, dimension reduction. Yes, Brendan.
I'm still lost by what you mean by bullet 2. What is the condition over, and what are you trying to find?
Yeah.
You just said it, but
Yeah, so the thing that I want to average over, I want to, given a fixed value of y, or a conditioned on y, I need to be careful. I'm in a stats department now.
over like the dimension of y? Or?
It's for a given value of y, so conditioned on y. So I'm going to set, let's say you have one active variable. You set that to 0.5. And now I need to average over all of the z's in order to construct this g. So that's the conditional average. So that was the picture in the movie when I picked points in the active variable, and then I chose a few points in the inactive variables to do a conditional average. Yeah. So you,
And P of z given y comes because we've defined P of x, and therefore P of z
yes.
comes out.
Yeah. This conditional average follows from the definition of rho. Yeah. Yep. Good questions. I appreciate the questions. Okay. So that's the big idea. Let's check out integration, and I'm doing okay on time. So how are we going to? And again, I want to reiterate this caveat that the integration, the optimization ideas are still emerging. What that means is, if some of you ICME students are interested in working on some cool ideas like how to integrate functions using zonotopes and how to construct zonotopes and how to do that for optimization, there's still a lot of work to be done, and I'm happy to talk to you about it. So let's see what happens with integration. So here's my integral that I want to compute, the average of my quantity of interest from my simulation. Have any of you taken Amir Dembo's class on probability? No? Okay, well, top one, good. so this is actually called the tower property. So we take the integral over all the active variables of the conditional average, given the y's, and that's equal to this. It's a tower property of conditional expectations. And then you'll notice that this thing here is actually the g of y that we constructed before. So let's see if we can do the integration just on the active variables. Reduce the dimension and now do some kind of like really high order quadrature rule on the active variables. So we're going to estimate this integral over the active variables by evaluating the conditional average at some set of quadrature nodes and then figuring out what these quadrature weights ought to be. And now, like we said before, this is a conditional average, so we're going to approximate each of these g's evaluated at y sub i's by some kind of Monte Carlo estimate. So the g hat is an estimate of this g. So you can think of this as, you all know, if you've tried to do high-dimensional integration before, you've seen anisotropic tensor product approximations. This is like an anisotropic tensor product approximation where I'm going to do something that's really high order on the y's and something that's really low order on the z's. That's the idea. And I feel like I can get away with that again because along the z's, my function does not have much variability. Right? Okay, so I love this picture. This is a picture of an active subspace exploiting quadrature rule. So the outline here is that zonotope going from an 8-dimensional hypercube down to this 2-dimensional silhouette. I then built a design on the interior of this. I used Maximin design. I threw down, I think, 8 or 9 points. And then I sort of moved them around until the minimum distance was as large as I could get it. And now I can do a Delaunay triangulation. Now, Delaunay triangulations, you can't do them in high dimensions, right? But you can do a Delaunay triangulation in low dimensions, like on these active variables. So you do a Delaunay triangulation of these vertices with these points. Now I have a set of triangles. I can get the centers of those triangles. I'll use the centers of those triangles for my quadrature nodes. And then the colors here represent, I'm sampling the heck out of that hypercube, sending them all down through W1 to this space, and I count how many of those fall in each of these triangles. So it's not a uniform measure because that marginal density of the active variables is not a uniform measure. You can see it actually gets a lot smaller near the boundaries. It's larger in the middle. That's not an accident. But I just think this is a really cool picture. Okay, so that's the idea for integration. If I come back and give a talk later, I'll have some convergence plots. I'll show you that I can integrate in high dimensions with something that beats Monte Carlo. That's the plan, right? So, and if any of you want to work on that, then talk to me, because I think that could be really cool and powerful. Okay, so let's talk about optimization. This is, after all, the optimization seminar, and so I need to be very careful about putting my work in a box. And so I'm going to call this optimization heuristics, because it's not global optimization. I said something on Twitter about global optimization recently. I said global optimization is like homeopathic medicine. There are a lot of anecdotes about it working most of the time or some of the times, but there's not really any science to go with it. Wow, that caused a storm. Because there are people that really work on global optimization and they really try to prove things about global optima. And then there are people but then there are also people that work on things like genetic algorithms or evolutionary algorithms, which are sort of these meta heuristics for finding global optima of complex functions where, again, you don't know any structure. You don't know it's convex, but you still want to do some kind of optimization to get better than the point that you started at. And so those are heuristics. So that's really the camp that I want to speak to, is if you want to try to do some kind of genetic algorithm to find a better function value than you had before, then I'll tell you what, some people deride these methods by calling it throwing darts. You're just throwing darts at the input space. But I'll tell you what, if you're going to throw darts, you want to throw darts in low dimensions and not in high dimensions. And so this is the idea, that let's throw darts in the active variables and then see if that helps us out for doing better than what maybe a genetic algorithm would otherwise do. Okay, so this is the idea. Here's sort of the only thing that is remotely rigorous, is if I actually have I've gotten rid of the approximation sign here, that if f of x is actually a function of a few linear combinations, then we can say something. Now, then assume that I could minimize this function g of y over the space of y's. So this script y here is that zonotope, the space of the active variables. Then all I need to do, I can do any kind of regularization that I want to go from the low dimensional y's to the high dimensional x's. This is just written as a standard linear program where my coefficients, where my weights are 0, and any x in here, if this is actually an equality, then you'll arrive at the minimum. But beyond that, if those eigenvalues that you've decided correspond to the inactive variables, if they're small but not 0, which is what always happens, they're very rarely 0, and even if they are 0, it's very difficult to detect that they're actually 0, then this result is not of much worth other than to motivate some heuristics. Okay. The other problem with minimizing that g of y is that, so here I've drawn g of y as the conditional average, and if your domain is bounded and has sharp corners, and your original function is really nice, this one's a quadratic, we know how to minimize that one, that g function can still get kinks because of the corners of the domain. So your g function might actually not be differentiable, depending on how you construct it. So there are a few ideas there, but the real big takeaway idea, the thing that we're actually trying to use the most, is to use the active subspace to help find starting values for some kind of gradient-based optimization. Right? That if you can build some kind of low-dimensional surrogate in the active variables, you minimize that thing, that gives you better starting points for gradient-based optimization than randomly choosing points in high-dimensional space. That's what we're trying to do. Fingers crossed. Okay. So here's a big overview. We're nearly at the end. Big overview of active subspaces, that the goal of all of this work is to make intractable high-dimensional parameter studies tractable by discovering and then exploiting some kind of low-dimensional structure. Right? I truly believe that this work is going to find, it's already found several applications. It's going to find some application where the scientists are like, oh my gosh, I'm learning something new from this kind of analysis, and it's going to change the world. So stay tuned. We define the active subspace by the first n eigenvectors of this funny matrix, the average outer product of the gradient. I don't really have a name for it yet other than that. We need to compute that thing, so we do that by some kind of sampling, and then we want to exploit that to do approximation, integration, optimization, the things that are hard to do when you don't know any structure ahead of time and you're in high dimensions. And so here's kind of a reminder picture. Okay, so now we are at the choose your own adventure part of the talk. I have prepared 4 applications to talk about, and I will give you the choice about which one I want to talk, or which one I will talk about. So let's do it by a show of hands. I've got, this is related to the work with Trent and Juan and Honora M6, Transonic Wing design. So for some of the quantities of interest, we went from 60 dimensions down to 1. The High-Shot 2 scramjet from the PSAP project, we went from 7 dimensions to 1. A photovoltaic circuit model, we went from 5 to 1. And then just a really simple parameterized Poisson equation. You've all taken your PDE classes and passed your quals. So this one goes from 100 to 1, but it's a much simpler model. Okay, so A. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's strong. Strong showing for the Honora. Oops, that was it. B. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can't vote twice. 10. All right, we got 10 to 16. Anyone do photovoltaics? 1, 2, 3, 4, 5, 6. All right, we got 16, 10, and 6. And finally, simple Poisson equation. Margot wants to see the Poisson equation. Your vote counts for like 10, but even so, I don't think that'll make it happen. 1, 2, 3, 4, 5, 5. Okay, so the Aerospace Design Lab wants to see the Honora M6. Yeah, good job, guys.
Paul, can I ask a question? Sorry.
Yes?
When you go from 100 to 1 dimensions, doesn't that mean you have to integrate your conditional expectation over 99 dimensions?
Yeah, I'll show you that picture just because you asked. Yeah, formally, yes.
The more you reduce, the more work you have to do.
Formally, yes. But I'll show you why it works. Okay. Let's if I have time, I'll go through a couple of these. So here is a Transonic Wing, the Honora M6. As I understand it, it's a standard test case. This work was mostly done by Trent. It's run with the SU2 codes. It's SU2, not SU squared, by the way. There are 60 shape parameters on this wing that control freeform deformation boxes that change the shape of this wing continuously. We've got some gradients that are based on the adjoint, but they're a little bit noisy still. And then the quantities of interest in this case are lift and drag. Okay, let's just focus on this plot for 1 second because I want to tell you what you're looking at. On the vertical axis here is the lift of this wing. Okay? This is the lift computation from this wing, full CFD solve. You get one number that's lift. On the horizontal axis is a linear combination of the 60 design variables. Okay? And what you see here is this really nice, it's linear, but more than that, it's univariate. Right? This is a univariate relationship between a linear combination of the variables and that quantity of interest. And so now what we could do, we could use all that machinery to build an approximation of lift as a function of the shape parameters by a scalar univariate function of one linear combination of those variables. So I've got a bunch of these plots. What this plot means that into and out of this screen right now are 59 dimensions. You're just looking at all of them from one perspective. Right? And so what I'm showing here as we move from left to right is maybe we'll start at this one. This is the baseline design for that Honora wing. And as we perturb the shape parameters along a particular direction, so I move my shape parameters along this direction, which is the active variable, and this is what happens to the shape of the wing. What this means is that my lift decreases the most as I move along this direction of the vector defining the active variable. I can go the other direction, I can increase lift as much as I want, and this is how the wing deforms. So Trent showed a lot of other cases, which arguably are more interesting, but this is the one that ended up in the book, and I think, and this is pretty cool. Okay, same thing with drag. So the one thing that you'll notice is that univariate relationship is not nearly as strong. Right? Now, you could fit, if a statistician had this data, the statistician would be thrilled, but we're not statisticians. We don't really have noisy data, right? It's a computer model. If you run the computer model once at one value, one day, and you turn around and run it at the same place the next day, there shouldn't be any change. It's not some randomness or noise. But nevertheless, if a statistician had this and wanted to fit a univariate model, they would be very happy. So there's more happening here in those other 59 dimensions. There's other variability happening in those 59 dimensions. But this is a pretty good model to at least get at the insight of what's happening with this wing shape as we do this one-dimensional perturbation. Right? I've taken the 60 knobs that change the shape and I've compressed it into one knob, which is moving along that 60-dimensional space in one particular direction. And as I change that knob, this is what happens to the shape of the wing. It looks really similar to what happens with the lift, and that's because lift and drag are closely related. The one thing that you'll see happening is that the thickness of this wing changes more for lift as opposed to drag. So you can, if you stare at this guy, you can see that what's happening is that the wing is still changing in the tail, but also getting thicker. Pretty cool stuff. I think it's cool stuff. I might be more excited than Trent, although Trent's graduating, so we should all be very happy for Trent. Okay, high shot? Yeah? Okay, we'll do high shot, because it's next.
What did you learn?
What did I learn? In terms of the physics and the insight and the aerodynamics and the design sense, you should talk to Trent and Juan. What I learned is that there are really complex models that admit this kind of dimension reduction. And for me, that was a big win. That I can actually take this tool to a real application, or certainly compared to a parameterized Poisson equation, I can take this to a real application, and I might actually learn something about the application. I might actually provide value to the scientist. And for me, as a person that develops algorithms, that's incredibly important. So that's what I learned. All right. High shot?
Oh,
Yeah.
which linear combination did you choose?
Yeah, I didn't put the direction up there. I can show you those. I can show you the picture of the weights of the linear combination, and
how did you choose it?
I chose well. If actually, it's a good question. If the gradients had been perfect, then we would have done this same analysis of sampling the gradients, form this matrix, and take the dominant eigenvectors, or the eigenvectors that correspond to the largest eigenvalue.
You had a procedure.
Yes, yeah. Although in this case, it turned out that fitting a linear model of lift to those 60 variables did better because of the noise that happened in the gradients. So, and that's actually what happens in the next example too. So let me do the high shot example, and then we'll call it quits. How about that? Okay. So here we have a very expensive, complex, multi-physics simulation of a scramjet engine, three-dimensional compressible flow. There are shock trains showing up in this channel because this vehicle is going at like Mach 6 or something just tremendous. Once you get these shock trains set up, you inject a little bit of fuel and you spark it, and it combusts and it produces thrust. and you get this pressure at the exit of this channel, and this thing is just going to go really, really fast. The problem with scramjet engines is that if you put too much fuel in, then the combustion dies, the flow becomes subsonic, and the thrust goes away. So you can imagine driving down the highway, you're pushing on the gas pedal, you're accelerating, accelerating, accelerating. You get to a point on your gas pedal where all of a sudden your car stops moving forward. Right? It's bad if you're on the highway, it's worse if you're in a vehicle in the air. Right? And so the question that we had for this PSAP project was, given the variability in the flight conditions, what is the range of the exit pressures that we expect to see given variability in flight conditions, and does that get near this terrible threshold where the thrust is going to go away and our vehicle is going to die and collapse? So there are 7 parameters that characterize the inflow of this channel here. We don't have any gradients. We have very expensive function evaluations, and they're also really noisy because it's compressible flow solver. This is solved with a fixed point iterative scheme. And so here, again, on the vertical axis, I have the exit pressure. So the pressure, it's actually integrated over a small region of the exit of this combustor. And down here, I have a linear combination of those 7 parameters. And we run 14 of these expensive simulations in 7 dimensions and do this, what's called a sufficient summary plot. So this is stuff that's been done in regression and statistics for a while. You do a plot like this and it lines right up. And now, imagine you want to find the maximum exit pressure over all the inflow variables. Well, you go as far as you can in this direction until you hit the boundary. Same thing in this direction. You want to find the minimum exit pressure of this vehicle. You go as far as you can in this direction, and that's what we did for the project. Yes?
You only do the gradients to construct this. Here you have no gradients.
Right. So, I would write it down, but we're about out of time. So I can show you how, if you fit a linear model, the coefficients of that linear model can, if you normalize them, can be used in the same way as that first eigenvector. And that's actually what's happening here. It's actually what happened with the honor row wing also, because the gradients were so noisy. And so we just used that the first eigenvector, which we derived from a linear model. You make this picture, it lines up like that, and you get really excited, because right? you can exploit this dimension reduction. We tried a lot of things with this problem too. I can tell you those stories later. Okay. And for the 100 dimension, this is the problem that goes from 100 dimensions to 1. So if I need to compute a conditional average over variation that's like this, I don't need to sample it too many times to estimate that conditional average, because this univariate relationship between a linear combination of the 100 variables and the one quantity of interest that I had from this PDE was just so strong that this function is flat in 99 dimensions as soon as you find that direction along which it varies the most. Yeah. Because the error in Monte Carlo is related to the true variance. So if the true variance is very small, very, very, very small, then you can get by with very few function evaluations. Okay, we made it to the end. I just want to plug the code that's on GitHub. So I've been working very, very hard on some Python libraries. It's called the Python Active Subspaces Utility Library, or PAL. Good, okay. Somebody laughed. For the record, somebody laughed. Okay. It's almost at the point of release. It's not quite at the point of release, but it's on GitHub now. All the algorithms or all the code for running the algorithms, making the plots is there. Be happy to talk to you about it. I want to do some really special thanks before we end. I learned from a technology person that you really need to support your early adopters. So let me mention some of these people. So Juan Alonso just left. Trent Lukacic and the Aerospace Design Laboratory have been interested in this for the aerospace design problems. Gianluca Iaccarino and Johan Larson and Mike Emery. Johan's at Maryland now, and Mike is at Cascade, I believe, and the Stanford PSAP team. Was really excited when these tools worked for this problem. Mark Campanelli is at National Renewable Energy Lab, and Brian Zaharotos was my PhD student that just graduated, worked on the photovoltaics problem. Also want to mention Reed Maxwell and his students, Jen Jefferson and Jim Gilbert at the Colorado School of Mines and their hydrology group. We've been doing some geoscience problems with these methods. So these people, I wouldn't be here giving talks about this stuff if it didn't work for these kind of problems, and I wouldn't have access to those problems without these people and their willingness to work with me and put up with me saying, oh no, let's try it a different way or something like that. Okay, so now we're at the other Choose Your Own Adventure part where we do questions. So if you have questions, now's your time to ask. You're welcome to ask them. If you don't have questions, because I just went through it so fast, I've put several questions up here that I think are particularly insightful. You're welcome to ask any of the questions that I have provided to you. Again, I'm Paul Constantine from Colorado School of Mines and Applied Math and Stats. You can find all this work on activesubspaces.org or find me on Twitter at Dr. Polynomial. Thank you very much.
Well, thank you, Paul, for a very dynamic talk about some very creative and important work, I think. So let's
I'll consider that an endorsement, so thank you.
that's very promising. Questions?
Yeah,
I
Brendan.
was wondering, for any of the cases that you've done so far, were you surprised by the loads that were seen? Because I know, like, for example, in the owner on 6, you basically find an angle of attack mode, which would be
Right.
expected. In, like, the photovoltaic sense, was it, like, shocking that there was this nice one-dimensional representation, or?
It was shocking to me. There is this issue that physics problems often admit a really low dimensional parameterization. And I think this type of approach gets at those those parameterizations better than a lot of the other approaches that are out there. Better, in my personal opinion, better than sparse grids or better than low rank approximation. There are other people that have seen this structure in physical problems. There's a group in physics at Cornell that calls them sloppy and unsloppy models, that it's sloppy along the inactive variables and not sloppy but structured along the active variables. So there are other people that have seen this. So maybe I'm just surprised at how prevalent it is. Every time, there are fewer models where I haven't found some kind of insight into the model than there are models where I have found some insight. So I'm just surprised at how well it works. Yep.
Hi, Paul. Very nice talk.
Hi, thank you. Endorsement.
Yes, another endorsement. I noticed you had a plot that you showed that these zonotopes had slices that were almost circles.
Oh, yeah.
This is something that's generically true for any convex body in high dimensions.
Oh, that's
does this
cool.
help you any-
I didn't know that. Let me go back here. These images are large and take a while to get through. Where did those zonotopes go? These guys, right?
Yeah.
Yeah. So the caveat here is that I generated these figures using random matrices. So I found an orthogonal basis from a random matrix.
That's important.
Yeah, it's very, very important. In fact, the eigenvectors that come out of these physics problems have a lot more structure. I wouldn't necessarily expect to see this. You can also think of this as the cube being in general position, and that is not the case. If you had, let's say you actually had a parameter in your physics model that did not affect the model, then all the components of the corresponding eigenvectors would be 0, and then you would have a dimension where you're looking directly coordinate aligned, and you wouldn't even, you might not get a circle, you might get something else. So it's hard to find 100-dimensional problems in real physics. It's hard to find something that you can just turn up the knob that is dimension, other than things that are spatially discretized. And in those cases, it's hard to get gradients. So we're still trying to look for this picture in a lot of problems. Yeah, good question though. Isn't this cool? I think this is really cool.
How did you make this plot? There's a lot of corners.
Oh man, I'm not quite ready to tell you that. There's a guy named Fukuda who wrote a paper in 2004 that enumerated zonotope vertices, and I found a slick way to randomize his algorithm, and it's in my code. If you want to go find it on GitHub, you're welcome to look at it. But I don't understand what's going on yet. But gosh, I got all of these vertices for a 100-dimensional zonotope down to 2 in about 2 seconds. Cool. So I'm still trying to figure that out. I actually think that has some applications to things far beyond this work in compressed sensing and different kinds of areas. Yes?
Actually, 2 related ones. Have you looked at generalizations to, say, quadratic forms rather than linear combinations?
Yeah, that's a good question. I haven't, and the reason that I haven't is that inverse map. So as soon as I get values in the low-dimensional space and want to move back to the high-dimensional space, if I have a nonlinear map, then that becomes a difficult inverse problem. Even linear inverse problems can be difficult.
The other is, I'm a seismologist. Seismologists don't really care about scalar functions. They want, cyclograms.
Yeah, what happens with if you have vector valued outputs?
Yeah. Do you just do it coordinate-wise right now, or?
Right now I do coordinate-wise. I do each coordinate at a time. A lot of the math you can generalize to vector valued outputs as opposed to having a gradient vector. You have a Jacobian matrix, and you can go through the exact same procedure, but I don't know how to interpret it. It's unclear to me how to interpret the thing that comes out. I'm really interested in the case where I have a process, like a time-dependent process that also depends on parameters. And I want to see something over the entire time region or something like that. Great question. Any more? You guys have been sitting here for a while. Yes, Pietro.
Yeah, it's not clear to me in practice which is the computational cost and the dependence on the initial sampling. Anyway.
Yeah.
The 60 parameters wing, wing.
Yeah.
In practice, I mean, how many computation? I mean,
yeah.
How many computation can start from doing that?
So the method that I presented that sampled the gradients first in order to discover that active subspace, you have to sample the gradients some number of times. We came up with a nice theoretical lower bound that uses that non-asymptotic random matrix theory. People still have the question. I mean, that lower bound depends on constants that I don't know, right? It's a really nice theoretical result, but in practice, we end up using a rule of thumb that scales like log of the dimension. We multiply that times the number of eigenvalues we want to estimate and some fudge factor. So you have to sample the gradient. And if you don't have gradients, we analyzed this with finite differences where you have some inaccuracy in the gradient that goes away. And it's one of these garbage in, garbage out things. If you have bad gradients, then your eigenvectors are bad too. But really the first thing that we do, or that I do with most problems, is fit this linear regression line and use that, or linear model, and use those coefficients and do the projection for the sufficient summary plot. And if it lines up, then I get really excited. And if it doesn't, then I have to say, oh, can you get me gradients? Or can we try to do finite differences?
I think that anyway, some of the observation that you can have can be also strongly influenced by the initial timing. Because, for example, I'm just thinking about global optimization.
Yeah.
Then in a space of 60 parameters,
yeah.
you can have anyway some region that you're not just observing. And
yeah, I can't even think about regions in 60 dimensions. Like it explodes my mind, right?
I mean, you could not really capture some
yes.
regions.
Yeah,
initial sampling is not.
So yeah, in the formulation, we get to say, continuous and differentiable, and the derivatives are also integrable, and that's sufficient. When you actually go to sampling, it's got to be really smooth. It's got to be smooth enough for that sampling to work. There's got to be enough redundancy in those gradient samples. And if crazy things are happening in the corners, you're not going to see them because you never get to all the corners in high dimensions. With that said, there is the reason that the non-asymptotic random matrix theory works is because of a concentration measure phenomenon. So the Trope's work built these matrix Bernstein inequalities, which says that under these certain conditions where the gradient's bound or where the norm of the vector is bounded, you get these really nice results about the distribution of the eigenvalues and how far the estimates are from the true values that you want to that you're trying to recover. Great questions.
Paul, I have one quick question. Just before the slide that says optimization.
Yes.
Can you find it?
This one? Or this one?
Oh, back one. Back one.
Sorry, I don't have slide numbers for you.
Is it that one? What's the one before? Oh, well, sorry.
That's all right.
It's not what I remember.
Okay.
Oh, well, don't worry. Thank you. Paul. Well, let me say, I want to thank Ben Coleman, our video man. Thank you for being here, Ben. Thanks everyone for coming. It's great to have a crowd to come and hear Paul. Mostly I want to wish Paul very good luck with his book and with all the important applications that are just waiting to be treated.
Hope so.
Thank
Thanks, Michael.
you, Paul.
All right. Thanks.